Right. So to find maxima and minima, I have to take the derivative of the function and then set that derivative to 0. So I'm going to need df by dx from this particular function. It is a function multiplying a function, so I'm going to need my product rule infrastructure. Let me jot that in there. This is not a function in a function, neither is that, so I won't be needing any chain rule. So I just have to do the derivatives now. Derivative of a radical is 1/2 x to the negative 1/2. Leave the e to the x alone. Leave the radical alone. And the derivative of e to the x is e to the x. So here's where things get a little tricky. This was fine when you were doing derivatives, and that is the answer. But it's not particularly useful to me at this point because I need it to be in brackets that I can use to build cases. We're going to have to do some factoring. So the first thing I notice is I have an e to the x in both of these terms. So I'm going to pull that out. df by dx equals e to the x. What that leaves here is 1/2. And then x to the negative half, it's 1 over, because it's negative, square root x, because it's 1/2, plus this radical here. Okay. Now, I have a fraction, adding a fraction, so I'm going to create a common denominator so that I can collapse those fractions into 1. This side has a root x in the bottom that this doesn't have, so I'm going to put that in there. That's an extra factor of root x in the top. And I need a factor of 2 in the bottom, so in it goes. My next line then would be df by dx equals e to the x. 1 times 1 is 1, plus 2. A root x times a root x is just an x. All over 2 root x. And I can further factor that by writing it as an exponential part, the rational part, rational radical blend part, and the linear part. Now, why would I do that? Well, here I can see that I have 3 things multiplying each other. So in order to check my cases when I set this to 0, there's going to be 3 cases I have to check. Speaking of which, to get my maxima and minima, once I do the derivative and tidy her up, I have to set it to 0 and solve. So case 1, case 2, case 3. E to the x, can this equal 0? Or can this equal 0? Or can this equal 0? Those are the 3 things I'm checking. This has an asymptote running along the x-axis, so this is actually impossible. But if you want to convince yourself of that, you'll need the anti-function for e to the x, which is ln. So x would be ln 0. And if you try that, you get error. This one here, 1 divided by 2 root x. Well, you can't get 0 through division. It's not possible. But if you want to convince yourself, perhaps you'd like to cross multiply. 1 equals 0 times 2 root x. And 0 times 2 root x would be 0, and this is impossible. So that's no good. Case 3, I'm going to kick this 1 to the other side. And I'm going to divide both sides by 2. Now that one actually works. It gave me an answer that's a number, that's not an error, or something that's impossible. So here we go. I have found a turning point in this particular function. Is it a maximum? Is it a minimum? I don't know. And I'm not going to find out until I actually have the x-intercepts, points of inflection and vertical or horizontal asymptotes to actually get a sketch. For now, I'm just going to use this X to find out where it is exactly. So I have the horizontal information, I need the vertical information. So to get the Y value, I take this and I plunk it back into the function. F at -1/2 would be square root of -1/2 e to -1/2. So I put that in the calculator and I try to work it out, and I will find out that this thing is an error because you can't square root negative numbers. So even though there was a potential turning point, that turning point failed because of the domain of one of the pieces of the function. So if that happens to you, what you write then is, therefore, there are no turning points. So you might be annoyed that we did all that work to find out that there are none of them. But knowing that it can't do that is almost as useful as knowing that it can. If you were trying to sketch this, right, you start doing this kind of thing, and then maybe you tried to draw a tail, well, that's forbidden, because it's not allowed to do that. This function has to, if it's increasing, continue increasing forever, because there are no places for it to turn down. If it starts decreasing at the beginning, it can never start to increase again, because it's not allowed to turn. So that's what happens if you have one that falls in a domain error. I have one more for us to try, and hopefully we can find a max min on that one. So again, to get max min points, I have to take a derivative and set it equal to 0. So here we go, dg by dx. This is a function in a function, so I will need my chain rule infrastructure. Working from the outside in, the derivative of a ln is 1 over whatever's on the inside. And then the next layer in is an x squared plus 1. The derivative of that is 2x, just 2x. 2x plus nothing. Right? Derivatives of constants are just 0. So I have a function that is split into two different pieces already, which is handy. I have this linear piece, and then I have a composite rational kind of piece. In order to find maximum minimum points, I have to set this thing equal to 0 and find all of the x's that make that true. And I can see by this setup that I'm going to have two cases, either this equals 0 or that equals 0. Pop them in there. So case 1, case 2, either 1 over x squared plus 1 equals nothing, or 2x equals nothing. So in the first case, you cannot get 0 by division. It's not possible. But to convince yourself, you could do a little cross multiplication. And 0 times x squared would be 0, and that is impossible. Here, divide both sides by 2, I get x equals 0. Now that, like the last example, was a perfectly valid number. It's not going to infinity, it's not giving me an error. So I potentially have a turning point when x is 0 in this function. So the only thing left to do then is to put this back into the function to get the y value. So g, when x is 0, would be the ln of 0 squared plus 1. So g at 0 would be the ln. 0 squared is 0, plus 1 is 1. And if you get your calculator out, ln of 1 is 0. So there we go. This one did not produce an error. I found an x in one of these cases that would set the derivative to 0. And when I plunked that back into the function, I got a perfectly reasonable answer. So what I have deduced then is that g of x has a turning point at 0 on the x, 0 on the y. Is it a maximum? I don't know yet. Is it a minimum? I don't know yet. It could be a saddle point. I don't know that yet. I need all the other features about this function on a grid before I'll be able to make that determination.